Okay, so now we're going to start with our level 1 through 3. Now that you know more about transformations and how it connects to algebra and then also mapping notation, we're going to get started with our lessons. So in algebra, we didn't necessarily learn what a one-to-one function is, but what a one-to-one function is from algebra is when there's the same number of elements in the domain as there are in the range. For example, we did learn about functions, and so if I had something like, I remember these ovals with our domain being the left oval, and let's say as I had 2, 4, 6, and for my y values, my range, I had -1, 0, 1. So there's the same number of numbers in the domain as there are in the range. That would be a one-to-one function. As soon as I throw in an extra y variable, that would mean that this is not a one-to-one function. So that's from algebra. In geometry, we have something similar. A transformation is a one-to-one function, essentially. So a transformation is when you have the same number of pre-image points as image points on your figure. So a transformation, remember, is when we take a figure and we move it or we make it bigger or smaller. The transformation maps the pre-image to the image, okay? But there is a one-to-one correspondence between the points in the pre-image and the points in the image. So if I started with a triangle, I'm going to end up with a triangle if I transform it. There is no way that you can start with a triangle and then end up with a quadrilateral and have it be a transformation. That's not a transformation. So there's always the same number of points on the pre-image as the image. So if we look at number 1, this is similar to like something that we would have seen in algebra. The same number of points in set A as in set B. This is a one-to-one function in algebra. Whereas in number 2, there's 3 points in set A, but there's only 2 points in set B. So for algebra, this is not a one-to-one function. So if we were back in algebra, we can determine if something's a one-to-one function versus something that's not a one-to-one function. Now number 2 is still a function, it's just not a one-to-one function. All right, so then connecting this to geometry, number 3, geometry, I started off with 4 points in my pre-image. My image now has 4 points. So instead of saying that this is a one-to-one function, we call this a transformation. And in number 4, if I start off with 4 points and I wind up with a shape that has 3 points, this is not a transformation at all. So in order for a transformation to take place, we need to have the same number of points in the pre-image as we do in our image. If you need time to pause the video to write this stuff down, I would highly encourage it. But moving on, so we know what a transformation is. There's specific types of transformations. There's isometric transformations and non-isometric transformations. And we're going to learn the difference between the two, and you will need to know the difference between the two. So isometric transformations can also be called rigid motion transformations. Rigid motion transformations, or isometric transformations, are transformations that preserve distances, angle measures, and parallelism between the pre-image and the image. And we are going to learn what each of those things mean in a little bit here. But basically, an isometric transformation is a transformation where no size change happened between the pre-image and the image. So we took a triangle or a figure, it doesn't have to be a triangle. We took a figure and we just moved it to a different location on the graph. No size change occurred, we just moved the figure. The three isometric transformations are translations, which means that you just take a figure and you slide it. So for example, if I have this triangle and I just decide to slide it over on the graph, that would be a translation. We also have reflections, which are isometric. That's a flip. So for example, if I took this triangle and I flipped it, that would be a reflection. And then lastly, a rotation is just we turn the object. So I take this triangle and I turn it. All right, that's a rotation. So all three of these are isometric transformations. So what that means is that they preserve distances, angle measures, and parallelism, which again, we'll talk about what that means in a little bit. But let's look at each of these examples of isometric transformations. So in this first example, what happened between this five-sided figure and this five-sided figure is we just turned it. So this would be an example of a rotation. In the second example, what I did for my first triangle to get my second triangle, my pre-image and my image, I just slid it across to a different location. So that's a translation. And then lastly, this example here, to get from my pre-image to my image, what I did is I flipped it around. So that's an example of a rotation. And now we learned mapping notation, and these are some examples of mapping notation. Notice again that the capital letters are just the name of the transformation. It doesn't mean anything. So this would be called transformation T, transformation G, transformation B. It does not mean anything. And these are just examples of rotations, translations, and rotations. Now, we will learn more about the different types of rotations, or sorry, I wrote rotation here. This should be reflection. I apologize. I think I said reflection and then wrote rotation. All right, so we will learn this many different types of mapping rules, but the ones that you might get mixed up are the rotations and the reflections. So this is actually an example of a rotation, and we'll learn the different mapping notations and the different kinds that can happen. But this is a rotation and this is a reflection. They look kind of similar of what happened. But you will have to know how to do a reflection, how to do a rotation, and how to determine whether mapping notation represents a rotation or a reflection or a translation. Now, a translation's easy to recognize because with a translation, you're always adding or subtracting a number from your X and Y value. Whereas with the rotations and reflection mapping notation, there's negatives thrown into the mix. Sometimes you will have to flip your X and Y value around, and we'll learn later the differences between how to determine if something's a reflection and how to determine if something's a rotation based on the mapping rule that we see. But that's it, isometric transformations. Now, a non-isometric transformation is a transformation that required a size change from the pre-image to the image. And these transformations do not preserve distances, angle measures, or parallelism. The two types of, this should say what are the non-isometric transformations. which in yours, it is fixed. So the two types of non-isometric transformations are stretches and dilations. So what a stretch is, for example, let's say I have this triangle here, and I take this triangle and I decide to just stretch it like this. So you can see that not all of the sides grew by the same amount. That's a stretch. Now a dilation would be, I have this triangle and all three sides are growing by the same exact factor, or the same exact amount. You can think of when they dilate your eyes at the eye doctor. Everything's growing in the same proportion when they're doing that dilation. So these are examples of non-isometric transformations. In the first example, it looks like we took this figure, this pre-image, and we made the size increase, and it looks like all three sides are growing by the same exact amount, so this would be an example of a dilation. Whereas in the second one, FG stays the same length, so this can't be a dilation, this would be more of a stretch. Same with the next example, LK and MN stayed the same exact amount, so this is a stretch as well. Now, when I say that your all dimensions grow or decrease by the same factor, that is when you're multiplying both your x and y value by the same number. So if you see in your mapping notation rule that both x and y are being multiplied by the same exact thing, then that would be an example of a dilation. And then if they're not being multiplied by the same thing, if they're being multiplied by a different factor, then that would be an example of a stretch. Now, if I'm multiplying x or y by 1 or -1, that means that you're not doing a size change there. So you can multiply by 1 or -1, that's fine, but anything other than 1 or -1 being multiplied by x or y would be considered a size change. All right, so now I talked about, that we're going to talk about what distances, preserving distances, angle measures, and parallelism means. So those are the three isometric properties, and we're going to talk about what that means. So I'm going to, it may be helpful for you to draw yourself a figure. And so I'm going to clone this figure because an isometric transformation means that your pre-image figure and your image figure would be the same exact size because no size change occurred. And then we're going to talk about what each of these things means. So I'm going to label this ABC and triangle A prime, B prime, C prime. All right, so what it means for distances to stay preserved is that the lengths of the segments are all the same. So what that means is that the length of segment AC and A prime, C prime are still the same. The length of AB and A prime, B prime are still the same length. They don't change. And the length of BC and B prime, C prime are still the same length. What it means for angle measures to be preserved is that the angles stay the same. So angle C and angle C prime are still the same angle measure. They're congruent. Angle A and angle A prime are still the same angle measure, so they're congruent. And angle B and angle B prime are still the same angle measure, so they're congruent. And then what it means for parallelism to be preserved is that segments that were parallel are still going to be parallel. That doesn't necessarily mean that AB and A prime, B prime are parallel. That means that, for example, if I had this quadrilateral here, and this quadrilateral here, these two are parallel to start, and they still stay parallel to each other at the end. And then these two were also parallel to start, and those same two sides stay parallel at